Hey there, good to see you again. Here we go into a great chapter of calculus. This is known as series and tests for convergence and divergence. And we're going to start out with a lesson on sequences, and then later on in this same lesson, an introduction to what a series is. So without further ado, what you're about to learn is, as I like to put it, some very rad fundamental tools of mathematics you're going to use again and again, especially if you go into higher level math. So what is a sequence? So the first thing we should start with, a sequence is a list of numbers, often with a pattern. And so what that means is it could be something like 1, 2, 3, 4, 5, like the basic whole number sequence. It could be something really complex. We'll take a look at everything in between too. Sequences consist of terms, starting with the first term going up by 1. So every term number goes up by 1. That doesn't mean that a sequence goes up by 1. I'm just saying the term numbers do. So a sub 1 is term number 1. That would be 2. The number 4 is the next term in this sequence. That's term 2. Term 3 is 6. Term 4 is 8. So the term numbers always go up by 1. But the actual terms themselves can go up or down by any number of values. So 2, 4, 6, 8, 10, and it goes on and on and on and on. Now these sequences can be infinite. They can keep going on to infinity, or just keep going on and don't stop, or they can be finite. We could do 2, 4, 6, 8, end it there, and that would be a finite sequence. So what we're going to look at with some of these sequences is our ability to find what is called the nth term, and I'll go over that in detail in a later video. Here, it's not so bad. We're looking at this, and it seems like what we're doing is we're multiplying the term number by 2, almost looking at it as if this is your y value and the 1 is your x value. This 2 is your x value and the y value is 4. So I multiply every term number, we call that n, by 2. So 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times whatever the term number gives you the term itself. Not bad, right? So that's it. That's an introduction into what a sequence is. A list of numbers, often with a pattern. And what we're now going to get into in this particular lesson is just being able to expand a sequence to the first few terms, and also being able to determine if a sequence converges or diverges. So we're going to look at infinite sequences. Let's talk about what it means to converge or diverge again. If you haven't already seen it, if you look at my improper integrals lesson in the end of chapter 8, you'll see convergence and divergence. This is the very same thing. To converge means to go to a set, constant, finite value. So even though the sequence goes on and on forever, if we eventually meet and level out at one finite number, the sequence is said to converge to that number. Diverging means we don't converge. It means we could continuously change values forever and ever and ever. Maybe they're going up, maybe they're going down, or maybe we're alternating between a few values. Let me show you what I mean. So this says expand each sequence to the first 5 terms. So to do that, we start out with term number 1. You're literally just plugging 1 into this. So a sub 1 would be equal to 2 plus negative 1 to the 1. Negative 1 to the 1 is negative 1 plus 2 is 1. And then a sub 2 would be plugging in 2 into this. That'd be 2 plus negative 1 to the 2. Well, that's 1, negative 1 squared, plus 2 is 3. And then a sub 3 would be equal to 2 plus negative 1 to the 3rd. And that's going to be equal to negative 1 to the 3rd is negative 1 plus 2 is 1. And then a sub 4 is 2 plus negative 1 to the 4th. So the math's not that bad at all. This simplifies to 3. A sub 5 is equal to 2 plus negative 1 to the 5th. And that is equal to 1. And it keeps going on and on like that. So this is determine if each sequence converges or diverges. Well, I like to write this out in one list. 1, 3, 1, 3, 1, and so on and so forth. This sequence continuously alternates between 1s and 3s. It will never converge on one set value. Even though we've got a 50-50 shot of being 1 or 3, we don't ever converge on one determined finite value. So this diverges. Now, how do you tell if a sequence diverges or converges? Like using algebraic means? Basically what we're doing here is we're taking the limit as n goes to infinity of a sub n. And in this case, it does not exist. And because it does not exist, we diverge. So that is the main question here. Does the limit as n goes to infinity converge or diverge? That's what you're taking. If you get a limit, and it's a fixed limit, we converge. If you don't get a fixed limit, or that limit does not exist, we diverge. Not so bad. All right, let's keep rocking and rolling. So here's what we've got. T sub n equals 5n over 2 minus 6n. We're going to expand out the first 5 terms and see what it looks like. And this time I'm going to do it just horizontally. So I'm going to plug in 1. I get 5 over 2 minus 6. That would be negative 5/4. That's a sub 1. Then I plug in 2 and I get 10 over 2 minus 12. So 10 over 2 minus 12, not so bad. I'm just going to write it like that. We'll simplify it in a little bit. Then I plug in 3. I get 15 over 2 minus 18. That's negative 16. And then plug in 4. We get 20, 5 times 4, over 2 minus 24, which is negative 22. And last but not least, the 5th term, plug in 5. We get 5 times 5 is 25, over 2 minus 6 times 5 is negative 28. And I'll simplify this one down here. I don't know why I didn't. That'd be over negative 10. Now we can simplify some of these down. No need to. I'm just going to leave it like that. Those are your first 5 terms. Determine if the sequence converges or diverges. Now, just taking a look at that, it looks like the fractions start out, they're all negative, but they're getting a little bit less negative. Like the fractions are getting a little bit smaller. To determine if that's true, we take the limit as n goes to infinity of the actual sequence, which is 5n all over 2 minus 6n. Take the limit like normal. And if you have trouble remembering limits, go back to my chapter 1 videos on how to take limits at infinity. All right, it'll help you out tremendously. So here we take the limit as n goes to infinity. We've got 5n over minus 6n. If you remember, we look at this and say, well, that's approximately like the limit as n goes to infinity of 5n over minus 6n, the two highest powers there. N's divide out, and you're left with negative 5 over 6. So yes, the sequence converges. And not only does it converge, it converges to the number negative 5 over 6. All right, we'll take a look at this one. Again, we'll do the first 5 terms, plugging in 1 first. So 1 squared is 1 over 2 to the 1 is 1/2. 2 squared is 4 over 2 squared, ends up being 4 over 4, or 1. And then 3 squared is 9. All over 2 to the 3rd is 8. And then we'll go to this third one. 4 squared is 16. 2 to the 4th is 16. Interesting sequence indeed. 5 squared is 25. 2 to the 5th is 32. And it keeps on going on and on. But those are the first 5 terms of this infinite sequence. So do we converge or diverge? To figure that out, I will take the limit as n goes to infinity of the sequence. That's all you have to do to figure out converge or diverge. Again, take a limit. So n squared over 2 to the n, we can do this one mentally if we think about it. N squared is fast, but 2 to the n is far faster. So this thing is going to go to 0. Now, if you don't believe me, we can use L'Hopital, right? We get we get infinity over infinity when we plug in infinity here. The limit as n goes to infinity, we get 2n over, and the derivative of 2 to the n is 2 to the n times ln2. All right, so that's still infinity over infinity. It's a funky looking infinity right there. And then that means we get to take L'Hopital again. So you don't have to use L'Hopital here. Like I identified in the beginning, 2 to the n is going to far outrace n squared. This thing's going to 0 eventually. I'm going to show it here. We'll take a derivative again of the top and bottom. That'd be 2 to the n ln2 times another ln2. Now when you take this derivative, it's 2 over a massive number, which is 0. And so since we go to a finite number, this sequence converges. Not bad. So you take the limit as n goes to infinity of the sequence. If we get a limit, the sequence converges to that limit. If we don't get a limit, or that limit is undefined, in other words, it doesn't exist, we diverge. All right, let's check out one more general message and then we'll call it a video. In general, as n goes to infinity, n factorial will always be more than some kind of power function, which is always going to be more than your basic your basic polynomial function. And let me show you what this means, and just trust me when I say this is going to really help you out down the road, including now. In fact, in that last problem, we could have looked at this and said, oh, n squared is far less fast as 2 to the n. So as n goes to the infinity, this is going to go to 0. So let me show you why that makes sense. Let's take 2 for example. So if I set a equal to 2, n factorial is still n factorial. This would be 2 to the n, and this would be n squared. And you might be like, well, how is this true? Well, remember, we're looking at it as n goes to infinity. So n factorial, and we'll do a review of what factorials are in a later video, but remember, just real quickly, factorial is n times n minus 1 times n minus 2 times n minus 3 times, and so on and so forth, until you get to 2 times 1, all the way down at the end. So that's a pretty big number. That's what this is right here. That's n times n minus 1 times n minus 2 times dot, 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 dot. And that's going to be more than 2 times 2 times 2 times 2, which is more than just n times n. If you think about it, this is infinitely many 2's, right? Infinitely many of them. That's way bigger than two numbers being multiplied by each other. So like if you get out to like the number 1,000 for n, 1,000 times 1,000 is big. 1,000 2's being multiplied by each other, way bigger than 1,000 times 1,000. And then this, if we have n equals 1,000, or n equals infinity for that matter, all of these numbers that we're multiplying are going to be each greater than 2. So now you're multiplying infinitely many numbers, most of which are more than 2, making this greater. So as n goes to infinity, n factorial is far greater than a power function, or I should say an exponential function, which is far greater than a polynomial. All right, that's it for this video. I wanted to show you that generalization, the big idea. To figure out whether or not a sequence converges or diverges, all you got to do is take the limit as n goes to infinity. If the limit exists, we converge. If it does not exist, we diverge. See you in the next video.